Hello, welcome to this presentation on the inverse form module of C++. In a few clicks we will show this functionality, how it works. And for being comfortable with calculation, the best way is to generate a file of normal impedance measurement, and then after that to submit this impedance measurement to inverse form solver, and to verify that the inverse solver is able to deliver a porous material that is able to reconstruct the submitted complex impedance. For doing that, we will just experience with C++. I have prepared some file. So we go to the database under porous material property, and I have generated polyester form. This polyester form has a mass density of about 30 kg per cube meter, a very strong Young modulus, 6.8 E8, so 600 megapascal, which is quite stiff here. A flow resistivity of 13,500 Newton second per meter square. A porosity of 0.98, a tortuosity of 0.17, a structural loss factor of 0.1 for the solid phase. Associated to the 608 modulus, we will have a Poisson ratio of 0.35. Viscous length is 8 E minus 5, and thermal length is 16 E minus 5 meter. We use a generic hair as usually. You see that compared to previous versions, the shear modulus now is gray out, to indicate that it is generated from the Young modulus and the Poisson ratio, assuming an isotropic structural phase for the material. Previously it was let open, which may be confusing for some people. Then I click cancel, so this material has been generated, and now I'm building a different trim. And you see a collection of trim. So, well, as you have many parameters to identify for porous materials, there are 9 parameters. The best way is to submit to the solver several impedances. Or normally you should acquire this impedance using a Kunst tube. You make several measurements with some sample of different thickness, and then you load this impedance in C++, and the inverse solver will deliver you the corresponding material. Then for simulating this test process, I have created different foam trim. For example, a 10 millimeter there, 100 millimeter, 50 millimeter, so different polyester one. So if I just limit polyester name, okay, reduce a bit the number of, and then you have all the polyester. I have a polyester foam trim layer I've generated from 10 millimeter, 5, 10, 20, 30, and 100, 150, and that's it. Okay, so a large range of polyester trim layer thickness, just a layer of polyester. Now what can we do now is to apply them to some cavity. For example, here in this cavity I just apply the trim of 5 millimeter. I put 5 millimeter name here. Here I apply to this cavity the 10 millimeter trim, and so on. So I have here the
as you can see, the 20 millimeter, 30 millimeter, 50 millimeter, 80, 100, 150 millimeter. And after doing that, I have to set to plot the complex impedance of the trim. I have to set each cavity to calculate damping from trim acoustic treatment. If not, it just takes the damping from the damping spectrum or for the absorption file you put in your model. So you have imperatively need to set the cavity property to these things from trim acoustic treatment to get the correct output, which is the acoustic impedance. We have also to set the trim. We need not to forget that, it's very important. We need to set each trim to normal impedance calculation. And then a few words to explain how to do it. So normally, per default, the set is diffuse field calculation. That means random acoustic incidence on the porous material from any direction. And then your angle of incidence has a range from 0 to generally 90 degrees. This is a diffuse calculation. And in diffuse calculation, you need also to enable the diffuse field. That means the weighting, correct weighting for diffuse field. And also, generally, if you have a limited size sample, to enable the windowing correction. And of course, you could take a sampling of the angle between 0 and 90 degrees, and as default we have 30. And the number of frequency averages within each frequency band integrated format, so we have third octave per default. We can take several average inside each third octave band, and in that case, for going faster, because most of the time the trim has not really highly resonant behavior, we just set to one calculation at the central frequency of the band. So one calculation per band, 30 angle averaging in diffuse field condition. This is a diffuse field setting, but when you are in Kunst tube, you have to take care that you are just measuring one wave normal to the sample. And then you have to simulate this condition. This condition is simply to reduce the number of angle to 1, and of course to set angle mean and angle max to 0. And to disable all this correction only valid for diffuse field condition. And this is the right setting for the normal incidence calculation. And now, when I go back to my model, if I click here on the cavity, I can graph automatically the trim impedance. Graphing the trim impedance comes with two quantities. The module is plotted as default, but you have the real part and the imaginary part. The imaginary part is negative here, and the real part is here. Now, depending on the thickness of the material, for example, if I go to the thickest material, the normal impedance will change, obviously, depending on Biot's parameter, which are part of the material property. Then you see the module, and then the real part, and the imaginary part. So if we try to compare both to the previous, I close it, call it previous. So I have to plot it again, trim impedance, okay, tau G. Now I put this curve into here, and I can compare. So you see 150 millimeter, the impedance is, in terms of amplitude, is decreasing. Increasing, sorry, but on the negative side, its absolute value is decreasing. And the real has also quite strongly changed. Huh? So it's why it's important to submit to the inverse solver several impedance, because these changes are not depending on a single parameter, so you can
put more constraint to your inverse solver in order to get better result. Now, what we do with our results, so we can plot all this impedance and export them in a file. And I've prepared a file which I will show you. This file is in the directory of the test directory. Okay, that's going here in my hard disk video, and here we inverse from test. I have so different file with different number of layers to see the quality, the improvement of quality with various layers. Or the file you can build up is to submit to the solver. If I edit this file, we'll see it's very simple. You have a first line where you put the thickness with separated by tab. So I have 8 layers, 1, 2, 3, 4, 5, 6, 7, 8, up to 150 millimeter, everything in SI unit, and the frequency on the left column, and then real, imaginary, real, imaginary, real, imaginary values of all the 8 impedance. So I have 16 columns here, each number being separated by a tab. Very simple format. You can generate it from Excel file or just from a text editor. And then how to use this in C+. And then it's very simple. You use it at the material stage. The inverse solver will be called at the material level. Why? Because the solver is depending on the choose of a model for the material. You need imperatively to, if you want to inverse characteristics of the porous, to use a porous model. So in that case, in the porous part of the material database, we have this create poroelastic from experimental data. And then I click OK. And you see that I need to import my file. So I will import the file with 8 layers. This is the right file. Okay, now I load the data. I can see that my 8 thickness have been retrieved there, and then I click next. And then this is the main page where you set the inverse solver. The inverse solver is based on a kind of non-linear, it's a non-linear inversion based on optimization. And at the bottom you have some kind of Monte Carlo process on a population of sample. Population is just a material you create, in fact, and from this population each time you generate random data and then analyze all this population to find local minimum for optimizing the distance between the measured impedance and the reconstructed impedance from the material you identify. And then for being efficient, I need to give bounds to my different parameters. Typically, for example, if you know exactly the density, you can, this is the mean value, so the lower bound, and the upper bound or the max value of each of the parameters. And in between, the intersection of all this bound is the parameter space. And then what you will do is to define a bound. If the mean bound is equal to the max bound, in fact, the parameter will be deterministic. Its value will not change. If you don't know, you give a range. So you know that a porous material like polyester foam should be between, for the flow resistivity, between 1000, which is very low, and about 30,000, which is very high flow resistivity. So this is a bound. Tortuosity, we know generally it's between 1 and something more important. For porous, maximum is 2. Porosity here is between 0.8 and 1. Porous shape parameter is the bound is already fixed, is never changed, so we put it because it can be also be used for quite exotic material, this solver. But for porous, this is between 0.3 and 3.3. And this porous shape parameter is the relationship is related to viscous length and thermal length perturbation. The Young modulus, well, we put a bound between 1 megapascal and 1000 megapascal. The Poisson ratio, we put a bound between 0.1 and 0.4. If you don't know, you increase the range of search. This is Poisson ratio. The loss factor or the loss ratio is obviously always less than 0.5. The loss factor between 0.05 and 0.2, and the density we set it as default to 10 to 50. This is a setting. We have additional setting here, which is in fact the criterion we use for analyzing the data. Normally, it's integrated value of the difference of the average difference between imaginary part and real part of the impedance between. So it's the average of the difference of the reconstructed impedance value and the measure value, but in real part and imaginary part. So you have already two criterion, and this criterion is an average over the bound of this difference. And we try to minimize this distance between the measured and reconstructed impedance. In fact, if you think most of the sensitivity more or less in the high frequency or in the low frequency, you can play on this real part and imaginary part gain factor to put a slope on your average. In fact, you give more weight to high frequency by increasing, giving a positive dB gain to the real part or the imaginary part, or gain less than 1, so you put minus 10 dB, and in that case, the low frequency, if you put minus 10 dB, will be boosted by 10 dB. If you put positive gain of 10 dB, the low frequency will drop down. In fact, it stays the same, but you increase the high frequency. So positive gain means I put a slope, positive slope on the frequency when averaging my criteria. So my criteria will be weighted by differently by frequency. Per default, you need to put a flat average on the both criterion, so all value in each frequency band are considered same weight, in fact. Right? Then this is the inverse solver. In the inverse solver, generally you have a population size. That means the number of samples you generate at the same time in iteration, in order to calculate some gradient and so on, and to make mutation of this population for best fitting the next step. Generally, if you increase, the calculation, the CPU which is needed, but at the same time, you are more likely to find a local minimum, which is more correct compared to if you reduce the population size. Finally, I found out best result could be about 100. Of course, if you increase exponentially the CPU. Per default, I use 100 maximum iteration. Of course, if the material is very exotic, you could increase the search time to verify that the convergence of the iteration. So at each iteration, there is some mutation, and the mutation method can be changed, selected. So you have best or you have random. If I look what we expect to have better results choosing best. Generally, choosing best means a little bit more time in the computation. Crossover method, you have two methods, uniform exponential. It's a bit complicated because you need to understand how the algorithms work. The same for mapping method. Nevertheless, more you know, more you can set precisely your solver to fit and to retrieve the data quickly and reliably. But if you are working, we are not a specialist of, when you use this kind of tools, we are not specialists of porous material, so generally you can play on population size. These two parameters, you don't really know how to set them at the beginning. We can play on the maximum number of iteration. We know that if we iterate more, we are looking for better solution. And you can play on the mutation method. So these three parameters are enough. And then the last parameter is that what it is needed when you optimize is to have some idea of the standard deviation of the output. This is very important. How to do it in practice? But in practice it's easy. I'm running the solver several times. So in C++, you provide a certain number of optimization and you compare the different results. Obviously, if you randomize the input on the output, if you don't reconstruct exactly the data, you will have some standard deviation, and from this amplitude, you know how much critical is your determination, or how much confidence you can get in the output. Well, now with default data, you can start directly, and then you start optimization, clicking this button when all these parameters. Here I will put a little bit more, let's say 6 run, and I start. So what is plot at the beginning? It's just the impedance, measured impedance. So you have 6 value, and then progressively, for each run, you can see the number of run here. You will try to match the different measure curve. You see that the matching is very good for the imaginary part. A bit more tough for the real part. It's more difficult to have a good matching on the real part. And we are waiting. Look at the standard deviation. If not so good, we can reprocess the data. And here we watch how many runs. So normally we ask for 6 runs. No, runs are completed. Now it's possible to click here and to look at the material. You see that if you remember the data, so the data for the we'll plot the data to compare with. You see that we can see the data in the background. So it was 13,000. We found 30,000.7. Very good result. So the standard deviation give us more, but we found 1.7. It was 1.7 for the tortuosity. We found 14% of standard deviation. Porosity 0.98. We found 0.0978, or nearly the exact result. And this is the most accurate identification. You see 1% here. Viscous length 8 E minus 5. We found E 4, 8. Okay, nearly same result. Also 2%. Thermal length 1.6, 1.3 here. Not so good. And you see the standard deviation is obviously a little bit larger. For the Young modulus, we are in the order of magnitude. 600, we find only 125 Pascal. So you see quite a big difference. And you see this is seen by the standard deviation, 127.
Position ratio, we see it was, well, we have 0.35, we had 0.3, well, okay. Loss factor was about 0.15, we found 1.19. And the density is about 50, and it was 30 in fact. Huh? So it's nearly, you see, some data are very, very good, some other are not so good. Huh? So what we can do is to restart. You see, when you click OK, you generate material. So new porous, first trial. Now we can effectively compare with what we measured. So the polyester foam was original polyester foam. Or we can try to put it together, and this is a new porous material. First trial, okay, 50, 30. Oh, this is good. 80, 1.7, 1.7. Well, this is big difference here. Oh, the shear was not an unknown, so this is a loss factor, the position ratio, the polyester foam at 0.1, the position ratio 0.35. So we are mainly difficulty 8.3, 8. Okay, that's a good number. And then 1.6, and it was for the tri material with trial. That one we get 1.3, 1.6. Okay, so also a bit of scattering. And now what can we do? We can just create a new one. Huh? So just load the same bulk data file. And then improve, putting 200 there. It was much longer calculation. And then we can use best 6, increase a bit the number of averaging in 200 iteration. So it was quite long. It should be a little bit longer. So we are just waiting now. And I will shortcut the video to not for you to wait the real time. Run 3, you can see that the convergence on the real part is much better in that case, by increasing the number of samples. We have run 4, you see that the convergence is pretty perfect for all frequency. We are very near the bias. At low frequency is very small. The imaginary part is really very well reconstructed. Generally, it's mostly the real part, which is more difficult. We are at run 5. Run 6 now. So the runs are similar, just to calculate standard deviation. So when you have a large number of samples, it's better just to make one shot, one inversion with a good accuracy. You see the last one is a bit more scattered.
for the first curve. The first is here the thinnest one. A bit difference, yeah. Well, we are at the last run. Generally, at the end, you have two different results, which are, and we take the best one. Generally, the most convergent one regarding the criterion, which is among the 8. There is one which is more accurate than the other, compared to the original target, which is the reconstruction of the impedance, measure impedance value, and there is a last, which in fact in which we start from the last. There is a 9 optimization, an extra one, which is done by tightening the search regarding the confidence interval. So we are reducing the confidence interval used for Monte Carlo solve in order to limit the scope of search in the last calculation. So a 9 iteration in that case. In fact, there was 10, so there will be an 11 one. And at the end, we take over the boss iteration. We take the one which has the minimal criterion. Now the run is completed. We can have a look. We have nearly same result for viscous length, all these parameters. The accuracy on Young modulus have increased a bit. Poisson ratio is reasonably dispersed, and the loss factor is well described. And the density, you see, we are much nearer from the truth. So you see that in this method, to calculate the optimized material, you need to generally increase the number of samples. Mutation method is not the best way, because if you take the best, you assume that you already find quickly some kind of local minimum, and then you go in a very particular direction. If you use random mutation, generally you don't respect at each iteration any predefined local minimum, and then you could, after a large number of iterations, converge to the good result. Okay, you see it's not difficult. It's much easier if you use a limb form, because the limb form is reduced to this parameter, to this plus the mass. So you have only 1, 2, 3, 4, 5 parameters for the limb form. So it's much easier to determine the curve with confidence. And of course, the best one is a fiber, where you have only the flow resistivity. Nevertheless, the fiber material is based on parametric equation. It's not a physical model, just measure data, in fact, at the end. So you need to have some fiber which fall into the character which falls into the range of classical fiber. If it is not a classical fiber, obviously you could not have a very good convergence between your measured data and your calculation, your identification process. Okay, that's it. And then now we say second trial. and then the material is generated in your database, so you can really create a new trim from it and then compare. It's what we can do, in fact, directly here to end up. If I go back to my page here, I will create a new trim, or with the last one, which seems better. I then generate, I duplicate one particular trim, for example, in the middle, 30 millimeter. Okay, duplicate. Okay, I'm duplicating this one. Then I'm changing the material to my second trial material with same thickness. And yeah, I put it's 8 impedance valued and second trial matte. You could use also user note to know to remember the origin of what you have done. Now I'm just putting this here in the 20, or we can duplicate that one. I will just duplicate that one, duplicate to make a new one, and then here I will put 20 millimeter from 8 impedance second trial matte. Right, so we just have to allocate the appropriate trim here. 20 millimeter second trial matte, okay. And then we can just plot, no, this one. Just checking I do the job correctly, yeah. Then graph the trim impedance, all right, and compare with the 20, that one, original one. Trim impedance, not that one. Trim impedance, all right. Now we can compare. You see the construction in terms of module is pretty good. Huh? If you look at the imaginary part, it's perfect. For the real part, you have a small bias, mostly, but very small. Huh? And if you look in terms of dB, so we have to put the scale, Y scale in dB. In that case, it's 10 log. You see the uncertainty is alpha dB, approximately on the measurement, compared to the exact. So it's difficult to do better. So you can generate material with confidence using this technique from generated from very simple measurement like a Kunst tube, sparing a lot of effort, because if you try to characterize each Biot material one by one, it should be a bit tough. I must say that I've experienced that in diffuse field conditions, the agreement is even better. Huh? This is normal incidence. Huh? Okay, matching. Okay, I hope you enjoy. Just to show you before to leave that we can do also for lymphome. Huh? In that case, you have this menu. No, this menu is working. The local menu is on lymphome. It's just works the same, huh? Except you have less parameter to characterize. The lymphome means you remove the effect of the material in the form. Generally, it's when you want to model fiber. Have no skeleton, so you can use a Biot model, but with no skeleton. So there is some process to remove from the Biot equation the structural part in order to have an equivalent porous material without any structural phase. This is a lymphome model. And if you want to use classical fiber material, you can do it from here. Just click in fiber and then create fiber from experimental data. It works exactly the same. And in that particular case, you have only one variable. So we can experience that the result is perfect, but okay, the most difficult case was treated here. It's Biot's material and it works fine. So enjoy with this new routine. It's part of the CFOAM software. It's called the inverse form function. And I hope you enjoy it. Thank you very much. Bye-bye.